Do you have some seats, do you?
You see my jacket? Anyone else?
Oh, well. It was interesting to sit down.
How you doing?
I'm trying to make spring happen in my yard.
You're becoming Italian, is what you're saying.
Yeah, it's the gardening fire. Has to happen soon. I've had enough of it.
We haven't had a winter.
Down low. Snowpack on the snow chart for Revelstoke shows normal or even a bit above normal. And of course, it's still building. Down here,
Which is,
I got it.
I drove to Kelowna on Monday. It was interesting to look at around Malacca. It's so low. And there's no snow anywhere.
Well, the build hasn't started for a while.
Well,
Swans in there.
Malacca and Salmon is not high ever. They have no snow, basically. Which is not a really good sign.
Yeah, like Malacca, like Eagle River, that'll rise according to the snow melt in the mountains. But out by Salmon there's not like high elevation snowpack to feed. Hear about that freshet.
A lot of unhappy agriculturalists, I'm sure.
I would want to have to send their water in California.
Oh, I don't
I
know.
do eat almonds.
Sure, let's do that. There's got to be a benefit to somebody somewhere.
And there should be some more dams there for it to make sure it gets there.
Let's see how much sand
You're laughing.
I,
A pipeline!
Here we go.
I know there must be a bunch of pipes somewhere.
Oil and water, you know.
Oil and oil, they don't separate, you
Send
can just
it down
send
the
them
same
both
place.
forward.
We had it over at,
Now, we think,
I don't actually know. Do you think it won't be any more than an hour? But you could stay. Yeah, I think it's like, yeah, no, I was part of the practice. Oh, yeah. Yeah.
we pay.
Oh, my pleasure.
I was away this week, and this Tuesday night, I will watch the video and then
But then you have to work.
you guys move my townhouse.
It's actually interesting to watch
I
and
know
catch
it
these
will be for
comments.
me, of course it will be. Thanks for the video and then it's the first time
I think there's a lot of nitty stuff going on, which I find very irritating. But, some of it is, I get it. We need some kind of housing services to be able to younger families, that it's going to be affordable, relatively affordable. And, yeah, and you know what? This is not a project that's going to be built anytime. It's not going to be completed in 10 years. People have 20, 30 years. So what that also means is that this project is going to be a real benefit to our construction sector and to our working class.
I'm personally interested in
What I did,
I think it worked relatively well because there were 200 people. And that's they spoke at the meeting. And then there are probably about another
have you heard about our fish course?
written comments that were submitted to council.
Yeah, I was thinking of an opportunity. If I was a fellow citizen, I would like to go to that interact with fellow citizens and chat and learn. And also, I need to read those reports. They could have put them up to 2 pages.
Of course it could.
Yeah, that's what I'm pressing for.
Then he mentioned that
Been
course.
around bureaucracy.
Yeah, it's called Ask the Developer. Yeah.
Oh, yeah.
Thanks.
I think in the end, well, it's going to go ahead, and I think in the end, it's going to be a big benefit to the community.
Yeah, we'd like to.
On just about every possible level,
Yeah.
including when it comes down to the sewers and that kind of
Got a
thing,
permit for that?
which were raised as, well, who's gonna pay for sewers? What if it's gonna happen about the new bridge that says, oh my God, let's not do anything, I wanna go hide my head.
And that's at Sulphur Creek.
I will watch the video.
Well, I gotta admit, unfortunately, you can't hear me on the video.
Oh, because you were commentating?
There were a couple moments when certain people got up and going, oh no, oh no, oh no, no,
I put money on
no,
knowing who those were.
no.
How many?
Folks who never saw a microphone they didn't like.
Yeah, so you can say max 20.
I didn't see you there, were you there?
Yeah.
Tuesday night? Well, it's best show in town.
What show was that?
What did Evan?
That was the public hearing for.
Is he going?
The Kenzie Landing.
Well, I mean, there's always a cutoff.
Big-
I'm surprised by that one. It doesn't really, 1,200 units, I don't, a real head scratcher.
Yeah, but it's not all at once.
Well, I don't care, 1,200.
Well, you know, what would you rather? Another, maybe 8 houses over that 14 hectares? They can only be owned by retired rich guys? You know? At what point does that help our economy and our community? That kind of growth doesn't help anybody except rich people.
Oh, there's a bunch of those lifeless mansions on the hill. I mean, I'm sort of in favor of those, but,
Yeah, but somebody wants to spend $650,000 to buy a piece of rock on the side of the mountain and then build their house, well, go ahead. But nobody should pretend that it's gonna benefit the community. And this is what bugged me about a lot of the people who showed up. They were flat out NIMBYers and pretended they weren't. But that's what it's about, protect my future.
Yeah.
I've got my piece of property and my piece of the future, and I don't want anybody to interfere with it.
Home at a decent hour. I know we're all busy. My name is Ian Drops. Thank you very much for coming. I work with the Columbia Mountain Institute, and we're very lucky to be hosting this talk tonight, followed up by a workshop which is taking place tomorrow. So what you're going to hear tonight is going to be a big summary, or a small summary, depending on how you look at it, of a greater workshop which will take place tomorrow. So you'll, I'm sure, hear a little bit more about that. What I wanted to do is mention a little bit about the Columbia Mountain Institute, who I work with. I have, you may know the Columbia Mountain Institute better when it was with Jackie Morris, who's right over here. So, a while ago, who I would say steered that ship, captained that ship for quite a long time and did a really excellent job. And since then, I've been lucky to take over for Jackie and now also work with Sylvia Wood. The Columbia Mountain Institute is an environmental organization. We are primarily a network who work with and for people who are doing applied ecology. And we work primarily with the focus in southern BC. But more and more our membership is expanding beyond, throughout BC, and up into the north and into Alberta. Altogether, our network expands to about 1,000 people. And what we do primarily is provide educational opportunities such as the one that's going to take place tomorrow, and of course talks like tonight, where we are giving professional development type opportunities such as courses, conferences, but also informal talks like this. So some examples of what we have going on this spring are, there's going to be a predator-prey dynamics conference that takes place in town here. Actually, it'll be up at Revelstoke Mountain Resort. And that's a 3-day conference, a fairly large event. We're going to have a grassland identification course. We'll have a fish ID course, which will take place in Castlegar. Every year we do an annual researchers forum where we have regional researchers from a given area who are invited to give updates on whatever their projects are at the time. And that's always a fun event. And this year it'll take place in Caslo. We do a number of statistics courses for people, biologists who are needing some assistance crunching numbers. So that's the sort of stuff we do. If that seems like it's of interest to you, then of course we'd love for you to join us, or you can sign up on a piece of paper back there to get announcements from us, and you'll be able to stay tuned on what we have going on. So I have some housekeeping things, but everybody here is from Revelstoke, and I don't think you need to know them. You're quite familiar. I want, before we really launch into the talks, is give some credit to our sponsors here. We wouldn't be able to offer this workshop or this presentation tonight if it wasn't for the Revelstoke Community Corporation and the Timber and Style Journals. So it is with great pleasure that I now get to introduce Utzig and Cindy Pearce. They have an incredible wealth of knowledge and are doing really, really interesting work. I am going to say a few words about Greg. I have, just so you know, very long bios for these people, and I'm told not to read them, but just trust me that they're incredibly experienced and well-accredited people. Greg Utzig is a conservation ecologist and land use planning consultant based in Nelson, British Columbia. Next door to he has over 40 years experience in environmental impact assessment, watershed analysis, marine vegetation mapping, habitat inventory modeling, and a wide range of activities related to forest management and biodiversity protection. In recent years, Greg has turned his attention to climate change in a big way, and we'll tell you a little bit more about that.
I'm going to end up standing here, so is that okay for you people on this side? Okay, good. Give me 1 second. Okay, so I'm going to talk about climate change, but I'm going to try and avoid talking about it in a big sense of what's happening all over the world, which is usually what you hear on the news or whatever, and it doesn't generally have much direct applicability to you in your own life. So what I'm going to try and do is present as much information as I can about the, what I'm going to call the Northwest Columbia or the North Columbia. But unfortunately, most of my work has actually been around Nelson and the West Kootenays, so I'm kind of translating some of it as it is applicable here in Northwest Columbia. So I also have to talk about my sponsors. Most of the material in here is from a project that Cindy and I worked on. This has been 4 or 5 years ago now, looking at vulnerability and resilience back in the West Kootenays. I was funded by the Ministry of Forests. I've also subsequently been doing a bunch of work on conservation planning around climate change, and that's funded by a couple of NGOs, WildSite and Conservation Northwest of the United States. Most of the information I'm going to be presenting isn't information that we collected ourselves, but information that comes from PKIC in Victoria, as well as some stuff from the United States and some stuff from Alberta as well. So, this is generally the outline I'm going to follow. We're going to talk first about just kind of generally what is climate change, what's happening, why is it happening, and then we'll get into more what it might mean for here in the North Columbia. So, who remembers there are 4 basic Greek elements? Got to put you on the spot right away. Now I know why you wear a suit, so see.
Fire, water, earth, air?
Exactly.
No.
So, very good. So, what we're talking about in terms of climate change is air, which is the one we always ignore. But think about it, just take a breath. Every moment we're breathing in that air, and yet right now we're using it as a dumping ground for waste, CO2 in particular, methane, and and that's what the issue is all about, is that, you know, you wouldn't think about throwing pollutants in the river, but every time we drive our car, every time we start the lawnmower, you don't think about putting it into the air, and that's what's going on in this dilemma. But the important thing is that what happens in the air actually affects all the other elements, and that's basically what I'm going to talk about tonight, is what we've been doing to the air is in fact going to affect these other three elements in a big way. So we could talk about growing emissions and emission scenarios, but I'm not going to talk about that. I'm going to try and just talk about locally. So if we just look at the Columbia Basin in terms of what our contribution to this problem is, this is the way it breaks down, is that all this brown stuff here is the industry and the stuff that gives us jobs. And this one for the tech coal operations has nothing to do with burning coal. That's just burning diesel to dig up the coal. If we threw the coal on there, then this pie would be tiny, what you see here compared to what the coal would be exported. But what we are doing is driving our cars, trucks, buses, we're heating our houses with propane or oil or natural gas. I don't think, you got natural gas here? Propane, yeah. So we are contributing a substantial amount, about 3.4 million tons. This is for the whole Columbia Basin, actually. So we are part of the problem. Just to give some feeling about what the problem is, I've found this video, which I think actually shows it better than anything else I've ever seen. So it's a bit complicated, but I'm going to explain it as it goes by. It runs for just a couple minutes. But what it's showing is, starting back in 1979, where the amount of carbon in the CO2 in the atmosphere was around 335 parts per million. And this line here, you'll see, will be going up and down. And this one will slowly accumulate up to where we are. It'll go to 2012, actually. It won't quite go to today. So it goes through year by year. And you'll notice it goes up and down as it climbs. And this red dot is Mauna Loa in Hawaii, which is where CO2 is sort of internationally measured. And anybody can guess why it's going. So this is showing you across from the Antarctica up to the Arctic. And why is it only going up and down in the northern hemisphere? Land, exactly. And there's lots of plants there. So every summer, our trees flush out, put on their leaves, suck CO2 out of the atmosphere, and so it goes down in the northern hemisphere. And then in the winter, as we heat our houses, burn coal and everything else, it goes back up again. And then in the summer, it goes down again. But you'll notice it keeps creeping up regardless. Whereas, as was said, the southern hemisphere has hardly any land, so there's not that much effect in the southern hemisphere. So we've been steadily rising since 1980. We're up to, what, year 2000, or 370. And each one of these points is a place where it's measured somewhere. So these little spikes is a big output from a coal-fired plant or something like that. So you could look at it in one sense, the Earth is essentially breathing, except that we're smothering it in CO2 now. And we get up here to today, almost. Don't quite make 400. We're actually now in 2016, we're over 400 now. This keeps going up. And in fact, it's going up at a faster and faster rate because we keep putting out more CO2. But if you look back in time, how significant is this? What was it, say, 50 years ago? So this is previous measurements to Mauna Loa. We go back to 1960, so we were down to, gee, it was only 310 then. And if we look at tree rings, we can go back, and it actually was leveled off previously. About 1600, we started the Industrial Revolution, which has basically really created this rise. We can look back further by looking at ice bubbles out of the ice in glaciers, or in this case, Antarctica, and see how significant it is 20,000 years ago. Well, gee, it was even less. So now we're back before the last glaciation. We're back a couple of glaciations.
this was the last big interglacial, but it only came up to about 300 or 280. So what it amounts to is that where we are today is greater than it's been in the last 600,000 years. And in fact, if you go back to the fossil record, it's probably greater than it's been for a couple million years. So it's a big experiment, one that hasn't been tested since before there were humans. And I think that kind of gives you an idea of where we're headed. And that's why the rest of this ends up being fairly significant. So, I think it's important to make the distinction between weather and climate. Weather is what it's going to do tomorrow. Like, can we go skiing tomorrow? How high are we going to have to go to fight snow? Or are we going to start in the garden tomorrow? But climate is a long-term average. And so when we talk about climate change, we're not talking about trying to predict the weather. We're talking about trying to predict major changes that occur over decades or centuries, not things that are day to day. And it's very important to make that distinction in that we're talking about major changes of long-term conditions. So weather is pretty variable from year to year. It doesn't matter whether you talk about precipitation or temperature, no 2 years are alike usually. But there's usually limits of what we call normals, and anything beyond that would be considered an extreme condition. There's also short-term patterns like El Nino, which we're in just at the end of a fairly major El Nino right now. They're kind of 3 to 5 year cycles in the weather. And then there's long-term cycles like the Pacific Decadal Oscillation, which run on a series of decades. And then there's long-term change. And that's what we're talking about in terms of climate change or climate disruption. It's a big long-term change. It's not a short cycle. But what you can see by looking at these other cycles is that sometimes the weather gets warmer really fast. Sometimes it actually may get cooler, but there still is this long-term trend. And that's a lot of things that you've probably read in the newspaper about the climate deniers saying, well, there was a big pause, climate change stopped. Well, it was just one of these small level-offs, and then the next 5 years we make up for lost time. And this trend has been fairly constant. Even if we look at, this is for the Columbia Basin, over the last century, the 1930s was a warmer time, then it cooled off, then it began to warm again, and then you'll notice this last 30-year trend, which is us, and it's actually steeper than any time it's been in the last century. And there is that long-term trend. So if climate was just increasing, if that was the only change that was occurring, is that we're getting increases in temperature, if you think about your distribution curve, this is like when you were back in high school. You know, you had this perfect curve where a lot of people got B's and C's, and there was the odd 2 or 3 people that failed, and there was a couple people that got A pluses. Well, what this is, a frequency distribution curve of temperatures. So most is around average, and then you get the odd really, really cold day and the odd really, really hot day. So if climate change was just increasing temperature, we just move that curve over, and we'd end up with almost no cold weather anymore, a bit more hot weather than we had before, and some new record hot weather, and no record cold weather. Which, to some extent, has been happening. If you look at, this is actually from Europe, and the reason I'm using European examples is they've got temperature records that go back 400 years rather than just 100 years like here. The coldest years in those 400 years were all before 1923, and the hottest years are all since 2002. So this mean has actually shifted quite clearly. So there's good evidence that this is occurring. But there's other ways that this curve can change as well. You can also change the shape of the curve. And if this happens, you end up getting less normal days and a lot more extremes out in the end. So we should be getting more extreme cold weather and more extreme hot weather. But that doesn't seem to be what's happening. If you've been following the news about extreme weather that we've been having, it's been one that's mostly on this end. But we are getting more extremes. So the other possibility, and this appears to be what is actually happening, is both things are happening simultaneously. Is the curve is changing and it's getting warmer, which is closer to what we're seeing today, which is we're still getting cold weather, but not as much as we used to get. We're getting a lot more hot weather and record hot weather. And there is actually some data to show that's happening. This is based on distribution of temperatures in the northern hemisphere. This being the 1950s, and this being the curve for the first decade in the 2000s. So it is widening out. Peak has come down. We're getting more unusual weather, and it's warmer. Now, it's these tails out in the end of that graph that end up being important, because that's what gives us these extremes. And these are the other things that have been picking up to back up the fact that the shape of the curve is changing. We're getting very unusual and more often heat waves, droughts, hailstorms, as well as extreme precipitation events. This is the situation that occurred when we had the floods in Calgary in 2013. It's the most expensive natural disaster in the history of Canada. It wasn't necessarily caused by climate change, but the intensity, the duration, and the damage caused has been shown to be contributed to by climate change. It's become more likely that kind of event will occur. And it's got this other quick little video that gives you an idea why that may be occurring. So I think most of you are familiar with the jet stream, and it's basically this current that goes around the northern part of the globe. And as temperatures have warmed up and Arctic ice has melted, the jet stream has started to change shape. You'll notice that it's getting, in this diagram, it's getting deeper and deeper. When it does that, it's able to suck warm, moist air out of the Gulf of Mexico, which is what happened with the floods in Calgary. And it also can pull down that cold Arctic air, which is that cold winter we've had in eastern Canada this year and last year, is due to this warping in the jet stream. But the other thing that changed on there was that those waves that go across North America, they move, as they get deeper and deeper, they move slower and slower. So instead of getting, and that's what carries our storms, the highs and lows across the continent. And as they slow down, instead of getting 2 days of hot weather, you get 5 days of hot weather. Or instead of getting 2 days of rain, you get 8 days of rain, which is basically what happened in Calgary. One of those cells just stalled over Calgary and it just kept raining and in the foothills. So what's happening more locally? That's kind of the big picture. Well, in order to talk about locally or in general about what's going on in the future, we need to have some kind of models that look forward. And all climate change models are just very complicated models that try and model all these different processes that determine what goes on in the atmosphere. There's evaporation, transpiration, precipitation, and, well, you can have a look at what's listed there. I'm not going to go into them in detail. And the way in which the models work is that you divide the Earth up into a series of pixels, and then you make those three-dimensional by putting layers into the atmosphere. And the model basically predicts in each one of those cubes what happens from day to day. And they'll predict forward for a century. So, you're talking about a large computer running for 2 weeks, and then you've done one set of models. Well, there's about a dozen different models internationally, and then you have to drive those models, and what's driving them is what people project we will do with CO2. If we were to stop CO2 tomorrow, that would be one scenario you could run, or the other scenario you could run is that we're going to keep producing more and more CO2 like we are now, and then you can run the model on that. Or you can assume that maybe we will actually do something in the next 2 or 3 decades, and we'll begin to reduce our CO2 emissions, and you can run the model with that and determine what the outcomes might be. So we're gonna look at a series of these outcomes for this area. Project that Cindy and I did a number of years ago in the West Kutenays, we chose 3 particular models, and this graph here, I have a number of graphs, and I'll try and make them as clear as possible, but everything above this line, the model is projecting that it's gonna get warmer. So you can see they're all projecting it's gonna get warmer. If they're to the right of this line, they're suggesting there's gonna be a percentage increase in precipitation annually. And if they're to the left, they're predicting it's gonna go down. Now, each one of these diamonds is a model scenario run with different assumptions about CO2 and a different model. There's about a dozen models here and 3 or 4 different scenarios, so we got roughly 40 outcomes. These are average for British Columbia, so the majority of the models are saying it's going to get somewhere between 5 and 15% wetter, and between 1 and 4 degrees warmer by the 2050s. So what we did for the work we did in the West Kutenays and the information I'll show here is we chose 3 models that were recommended that are kind of around the edge. So the answer could be any one of these, but by choosing these 3, we can pretty much assume the answer is probably somewhere between those 3, okay? So this is an average of a dozen of those outcomes just for looking at the Columbia Basin and looking at different seasons across the year. So what they're saying is that up here, we're looking at a 2 to 3 degree increase in summer temperatures, 1 to 2 degree increase in winter temperatures, and a 3 to 4 degree increase in summer temperatures, and back to 2 or 3 for the fall. In terms of precipitation, we're looking at somewhere around 10 or 15% increases in winter, spring, and fall precipitation, but decreases in summer precipitation of somewhere between 5 and 15%. So quite different summer outcomes, both for temperature and precipitation, which, when you think about it, that's a fairly ominous change, especially when you think about fire. So if we compare this is a different 15 more recent models looking at, what I did was ran for what I'm calling the Northwest Columbia. This is basically similar vegetation type, similar climate today in this region. And these are averages for less than 1,500 meters in elevation. So this is a summer temperature, average was around 14 at the beginning of the century, and as we've come up to now, we've already gained about a degree. And these are the projections for 2020s, averaging these 30-year periods, 2050s, and 2070s or 2080s were out here. And the reason there's 2 dots is that the bottom series of dots assume that we do something about our emissions. In other words, by 2050, we've probably done away with all of our emissions. The upper dots, or the upper squares, they assume we keep going as we are now. So we can have a difference. But we're already locked into a certain amount of heating by what we've done in the past. Winter temperatures, again, have risen a degree and a half, and are projected to increase 3 or 4 degrees over the coming few decades. And this is the annual average. Spring and fall are almost identical to the annual average, so I haven't put them on there.
Excuse me, Greg. When I started working on climate change, I thought 1 degree? Who the heck cares? 1.5 degree? Who the heck cares? How many degree difference do you think there is between Revelstoke and Vancouver in terms of mean annual temperature? Just guess.
2 degrees.
It's 3.
3?
It's 3. Okay? So big change in climate, small change in average temperatures. Really important message.
these are looking at seasonal precipitation. As you can see, there's a lot more variation in precipitation, and these are by decade, but there's a lot more variation in precipitation than there was in temperatures. Temperatures are fairly uniform when you average them out. Precipitation really varies year to year, and in this case, even decade to decade. The last couple of decades, we've had actually a substantial decrease in winter precipitation, whereas fall is running more or less the same, although it's quite variable. And then spring and summer have actually slightly increased until a decade ago, and now we're on a downswing again. What's projected in the future is actually an increase in winter precipitation, but it's not much more than the record that we've had before, back in the 1970s. Fall, a slight increase as well. Spring, slight increase, or at least holding the same. Whereas again, summer is indicating a likely decrease. Probably back to where we were in the lowest it's been.
That's actually, sorry to cut in,
Yep.
that's really interesting, the blue line there. I mean, that's the first real statistical sign of we're going to see something significantly changing what's been happening. See, data there doesn't align with.
Yeah, no, I was very surprised when I saw that as well, and I actually, this is out of a modeled system for British Columbia. And so I went and looked at the actual data because it looked suspicious to me too. And even, like, there's a huge amount of local variation. There's two stations in Rogers Pass. There's one at Rogers Pass and there's one at Mount Fidelity. One of them looks like this and the other one doesn't drop as much. And they're not that far apart. If you look at Revelstoke, it drops off like this. If you look at Micah, it actually went up. So it's highly variable. And I say this is an average over this whole large area. So it includes information from stations in Golden and Micah and Revelstoke, probably across. And so it's a regional average. But when you look at the other average, and I've looked at it for other parts of the region, this downturn in these last couple of decades is actually quite widespread. It's amazing how we don't notice it. Some people do, but.
Yeah, sorry to interrupt, but I was interested, do you think that's got anything to do with, I know we're looking at the Columbia Valley, and obviously there's been lots of changes with damming of the river. I've only been in town for a few years, but I've heard that since the dam was put in, there's been significant snowfall changes in town. There's less now than there was. Do you think that's got anything to do with it, or do you think it's just kind of year-to-year variation?
I just think this, but I'm working with Greg, but he's the main scientist, I'm just the adaptation girl. We posed that question to some climate scientists in 2006 and 2010, and the challenge is, if you remember Greg talking about the 1970 to now, about that's when the things turn up, well, that's exactly when the dams were put in. So the situation is what they call confounded. It's difficult to tell which is actually the cause, but the two, there's enough water that there's probably some relationship there. Fair?
It's fair enough. I would go a bit further and say that it may have had some effect, but when I look at the data from in the Rocky Mountain Trench, it has this same trend, so I wouldn't ascribe it to the dam personally. I'm not going to say the dam had no effect, but it didn't cause this. That's a wider, more regional trend.
Thank you.
Yeah. What it may have changed in Revelstoke itself is the fact that, you've got a body of water that's there that's warmer than it probably would have been if it was just the river. But if you think about the way the reservoirs run, it's almost always down in the winter, so it actually doesn't have any effect in the winter. So, this is another graph which kind of combines that impact of changes in temperature and changes in precipitation. This is what's called a climatic moisture deficit. So it's, as things heat up in the summer, there's evaporative demand that's placed on plants. As you know, if it gets hot for a week and it doesn't rain, you've got to water your garden and things start to wilt. Well, that's what this is measuring, is the likelihood of that occurring. And as you can see, the climatic moisture deficit was fairly high in the 1930s, the time that we knew was hotter and drier, and then it dropped back down to reaching a low in the 1980s, and now it's started to climb again, and it's projected to continue to climb substantially, well above what it's been in the last century, actually. Again, this is for the lower 1,500 meters. below 1,500 meters. So I think the important thing to note is that this blue line is, if we just think about temperature, is what we've experienced over the previous century in terms of a range of mean temperatures for the Columbia Basin. Already by the 2020s, which are only 4 years away, we're outside of what we've experienced previously. And by the 2080s, we're way outside what we've ever experienced. Like, we're talking about a big change from what we've known before. Whereas precipitation, because it's so variable, you know, you get a 15 or 20% increase in precip, and it's not outside the range of a dry year and a wet year, whereas temperature is moving fast. So what is this going to mean? I don't know how many of you are familiar with vegetation zones. You're familiar with the kind of vegetation around here. We're talking about big old-growth forests, usually cedar hemlock forests in the lower elevations. And in the upper elevations, you get into Engelmann species of alpine fir, like the top of Mount Revelstoke Drive. And then, of course, when you go into the Okanagan or into the East Kutenays, you get ponderosa pine or open grassland with large trees separated. And then, of course, you get into the Chilcotin, you get into real grasslands. So we're going to use these vegetation zones to kind of try and picture what these new climates might mean in terms of what might potentially be here. If you take a map of these zones, what they're called biogeoclimatic zones for British Columbia, which the southern interior, this light green color, is the interior cedar hemlock, and the purple is the Engelmann spruce of alpine fir, the upper elevation forests. And the more yellow and red are the grasslands and the open forests, and as you can see up the Rocky Mountain Trench as well. Each one of those zones has a range of climate characteristics. And if you group those different climate characteristics, you can look at the mean wettest month or the mean driest month. You can look at the difference between the wettest and the driest, or the warmest and the coldest. You can group them into things that are generally maritime or coastal and continental. In other words, this, the classic climate here would be Alberta and Saskatchewan, but some of the eastern parts and the northern part of the province is that kind of climate. Whereas the maritime, of course, is the coastal stuff right out here. So what we've done is, on this, and then we've got warmer stuff at the bottom and cold wet. So you can see the Peace River country up here, northern part of the province is more continental, and it tends to be colder, whereas the coastal stuff is warmer, and it's also more maritime. And we're kind of here, we've got some maritime characteristics, some continental, and it tends to be wetter, so we're still up here as well. Now, you can take any particular spot. This is based on probably a 1 kilometer grid over the province, so it's about 1 million points. You can take one point and say, okay, that's where it sits on the grid. And if you take your climate change projection models, you can say, well, that point fits on the grid here now, okay? Because there's been an increase in temperature. And in this particular case, a drying as well. And then you can go back to the map and say, okay, well, what kind of vegetation occurs in that climate today? Because this point over here has the same climate that's projected to be here in the future. So if we have interior cedar hemlock today, this point has moved from interior cedar hemlock to a ponderosa pine forest in terms of its climatic characteristics. Okay? Does that make sense? Okay. The tricky part is when it comes out into these white spots, and there's no place in British Columbia that has that climate. And then you say, oh, we have no idea what it's going to be there, what it's going to be like. But the models that we used actually went further and actually looked all over Western North America to try and find a climate that fit. And if you think about southern British Columbia and it's getting warmer, more than likely the climates that are similar to what we might have in the future are probably going to be down in the States somewhere today, if they exist. Okay? So we're going to look at what happens here in the North Columbia if we run that kind of model. And what I've done is run that for these three different scenarios. So one we're going to call hot and wet, one warm and moist, and one warm and dry, or hot, very hot and dry. So if we look at the warm moist one, which is kind of the optimistic one, there's not that much change. And this is what it looks like today. We had climates that were suitable for a wet interior cedar hemlock in the valley bottoms, and then an England spruce, and then alpine tundra up in the upper elevations. What this particular scenario is projecting for the future is that if we go, Revelstoke is just down here, we go north towards Micah. The bottom of the valley, some parts of it will be dry enough that we might have open ponderosa pine forests like you see in the Okanagan or Cranbrook. That kind of climate. I'm not going to say those forests are going to be there, but the climate that supports those kinds of forests is what it's projecting. The middle elevations, this light blue, is kind of a coastal transition cedar hemlock. So it's not that different from the forests we have here today, but quite a bit warmer. If you think about going on the North Shore above Vancouver, that kind of, they're not quite that wet. And the upper elevations are similar to the forests that we have in the lower elevations today. And all that Engelmann spruce and alpine fir forest that used to be at the upper elevations is gone. That climate has disappeared. And we have almost no alpine tundra or open parkland at the upper elevations, just a bit over here in the highest part of the park. And there we get this dark blue, which is the real coaster cedar hemlock type of climate. If we go to the hot wet model, it's wet enough that it overcomes this increase in temperature at the lower elevations, so we get a real dry grand fir cedar hemlock type environment, which is essentially equivalent to what's in Creston today. Creston and further south if you're driving towards Spokane. Mid elevations are that coastal transition cedar hemlocks up on the east side of the Cascades, and the very highest elevations are coastal western hemlock or maybe even mountain hemlock, kind of high elevation coastal kind of stuff. But again, you notice alpine is just very spotty now. And if we go to the very hot dry one, we get a really big change. We've got grasslands halfway to Micah Creek, or grassland environments, and we're not talking kind of like Osuyus. We're talking like Boise, Idaho. Like no trees in sight. Mid elevations, we're looking at something like Cranbrook or Kelowna. And the upper elevations, a bit of cedar hemlock, but it's quite a bit drier than even at the lowest elevations here today. And forget about alpine environments completely. So we're not saying any one of these is what's going to happen, but what we're saying is that the answer is somewhere between these three, probably. If you want to try and cut down on the variability and try and think, well, this doesn't really tell us much, it's all over the map. But if you look at it closely and think about it, there are two distinct things happening here. All three of the models are saying the lower elevations are going to get warmer and drier. It's just the only way the difference is how much warmer and drier, okay? Whereas the upper elevations, there is quite a bit of variation. So what I would say is there's pretty good certainty about what's going to happen at the lower and mid elevations, and a lot of uncertainty about what's going to happen at the high elevations. We'll just do the same thing for Revelstoke and south. This is the, and as you go south, of course, it gets even warmer and drier. This is the warm, moist one. We're looking at extensive areas around Revelstoke where we're looking at ponderosa pine type environments. And the upper elevations, again, it's just what we have at low elevation today would be what we would have at high elevation. This is for the 2080s, so we're a ways out into the future. The very highest elevations, we're getting some mountain hemlock, cedar hemlock, coastal kinds of environments. The hot, wet one, the lower elevations, we're still looking at getting that very dry cedar hemlock, grand fir, Douglas fir. A little bit, even with this one right around Revelstoke, we're still looking at grasslands, even though this is the wet one, because it's so warm that it doesn't matter if it rains that much in the winter. It's hot and dry enough in the summer that we're not getting trees able to grow. But because there's so much more snow at the upper elevations, we're getting actually an increase in the amount of alpine and mostly cedar hemlock type environments. This kind of gray that's going along the valley here is what's known as montane spruce. It's similar to the kind of mid elevations you get between Cranbrook and Golden. And the hot dry one, this far south, we're looking grass, pretty solid valley bottom grasslands all the way up to north of Revelstoke. and then the ponderosa pine type environments, and then cedar hemlock only at the highest elevations. So this one's pretty drastic, but what can I say? It's what the models say. So there are going to be some big changes. Where the model had to go to find those environments today, so what it's saying is that those grasslands today exist somewhere down here in the States. I'd have to look at the model and tell you exactly which one, but some of them are as far south as Kansas. Those ponderosa pine environments are coming from down in Oregon. It's the most similar climates, coastal transition. And ironically, the coastal western hemlock ones are not ones from the coast of BC, but they're from the coast of Alaska. Because they're at those high elevation ones, so they're actually quite cool, wet coastal western hemlock type environment. So, you can also run these models to look at the distribution of trees. If we take western hemlock, so the way this is colored, this is that northwest Columbia area, so Revelstoke would be right here, and mica right there. So the darker the green, and if it went to blue, but it doesn't go to that, except for right at the bottom here, the darker the green, the higher percentage of hemlock there is. So you can see hemlock is very dense in the lower valley bottom between Revelstoke and mica, as you all see further south as well. But it doesn't occur in the upper elevations. If we advance that to the 2020s, you can see it's beginning to spread. It's going into the mid elevations. And this is based on the environment, the kind of climate where hemlock grows today, and where that climate is projected to be in the future. And this is actually the average of 18 models. So this map on the right, what it's telling you is, if it's red, all the models say no hemlock environment. If it's dark blue, all 18 models say yes, hemlock would be there, okay? And if it's some of these colors in between, some of the models are saying yes, some of the models are saying no, so it gives you kind of a feel for what is the reliability or the uncertainty associated with these projections. So if we roll forward to the 2050s, all at once hemlock is moving up slope pretty quickly, or the hemlock